Hello, this is David Scher. I'm posting here right near the end of the semester in Physics 578, Medical Health Physics. I'm very, very close to the and I wanted to touch base, go over a little bit of information about shielding calculations for medical X-ray. Okay, and so I'm going to go into this quickly. Green, and this is what we're going to talk about: diagnostic. X-ray rooms and shielding specifications and how to determine how much shielding is required. So the reason we're doing this is we want to maintain exposed workers and the public within the maximum permissible levels, and beyond that, we want to maintain exposures as low as reasonably achievable. So we want to make our calculations with conservative assumptions, and we're going to try to be as prudent as we can with making sure we're providing adequate safety, but not overdoing it. Okay, so we have three radiation sources we need to address. First and foremost is the primary beam, and that's whatever is coming straight out of the machine without any shielding or attenuation. That's generally after that. That's what we need to evaluate. In addition, the patient and patient in particular is going to scatter the radiation, and that could pose a hazard to people around. And third is have a limited amount of leakage that's permissible, and so we need to take that into consideration as we determine what shielding is required. Okay, so the old approach was governed by NCRP 49 until a few years ago. This is my copy of the old approach. There we go. And I go over NCRP 49 because it makes it easier to discuss what's new NCRP 147. So the way things worked in NCRP 49 is that we make all of our calculations or all of our determinations based on this graph or graphs like this one, which show the attenuation. I don't know if it's easy for you to see, but these are curves of different, each one characterized by, represents a different tube voltage. This is 50 kilovolts. This is 70 kilovolts, 100 kilovolts, 125 kilovolts, 150, different tube potentials, and then what the attenuation is. So with added thickness, this is millimeters of lead, then the exposure that would be observed at a meter for the same workload, same so the output from an X-ray tube is proportional to the tube current and proportional to the time, and so it's proportional to the product of tube current and time. But the output increases as a square of the kV, approximately. And so the higher KVs are more higher KV photons, KeV photons, higher KV X-rays are more penetrating. So for the same amount of material, a smaller fraction persists for low energy, a higher fraction continue for higher energy. That should not be surprising. So the graph shows what fraction is attenuated at, uh, at what exposure level. This is R per MA minute. So that's tube current time product at 1 meter, and then how that varies with added attenuation. Okay, so so yeah, there's a graph very much like this for concrete in the NCRP report. Um, um, this is, so those are the most common. This is, so these are some, so this is the graph for concrete. I think it's visible there, yeah. So it's very similar. What you would do in the old day, under the old approach, and we'll go on to the next slide. What you do under the old slide is figure out what your MA minutes are going to be per week. Then we figure out you need to know what the distance you're going to your from your X-ray tube to the exposure point where someone might be exposed. So you look at a floor plan and you say the distance from the X-ray tube to the point where in the nearby room or the control booth or whatever point you're evaluating, the distance is whatever, 3 meters, 4.5 meters, whatever it is. You you have a W, you have the use factor. Use factor is uh, um, in an X-ray room. Sometimes we point the X-ray room to the north. Sometimes we point it to the south. Sometimes we point it from down toward the earth. It can be pointed toward different barriers. So we take the total workload that we have for the room. We multiply it by the fraction of time it's pointed toward the barrier we're now calculating. And then the next factor that's used in the calculation is occupancy. On the other side of the barrier, how much time do people spend there? So you can imagine that the amount of, if it's an office, people work there full time. The occupancy factor is 1. When the X-ray is working, you can assume that someone's in that room. If it's a reception, on the other hand, if it's a hallway, people just walk on by. If it's a restroom, people are only there for short periods of time throughout the whole year, not all 24 hours, 8 hours a day, 50 weeks a year. So there are factors, and I'll show them later for NCRP 147, but there's an occupancy factor that figures into this calculation. So for primary radiation that's passing through, the radiation exposure, this is the milli per week, is this factor K that we saw on the graph, however many reds per minute, per MA minute. So that's what K is. W is the workload, how many MA minutes per week. U is the use factor, what fraction of the time is it pointed toward the barrier we're thinking about now. T is the amount of time people spend on the side of the wall. And D squared is the distance to the receptor where we're calculating the dose. Now, this is what the exposure rate is. This is the MR per week in the old system. So we can say, let's make the dose rate, the doses delivered per week, equal to some limit, and we're going to call it P. And we'll talk a little bit about what P should be. In the old days, it would be 500 millirem in a year or 10 millirem in a week. So in the old NCRP 49 days. So based on that, we can figure out what K is. K is equal to PD squared over WUT. Now, one reason I go through the old way of doing things is because you see this formula in a lot of places. There's a formula sheet that the American Academy of Health Physics gives to people who take the exam to remind them of formulas that they should know how to use. This formula is on that sheet. So it's been around for a long time. So PD squared over WUT, knowing what the symbols stand for and how to calculate it. So what we do is we calculate K. We take our P, our D squared, divide it by W, U, and T. We get some value. Then we go to our graph and we get the K. That's K. We get our K and we say, okay, PD squared over WT. Let's say K is 10 to the minus 4, and we're operating with a 100 keV extra 4. I would find where it reaches 100 kV X-ray machine. I would go down and I would say that's 2¼ millimeters of lead, and that would be the amount of shielding I would for the primary beam. So that's how the old system worked. This system isn't so different, but conceptually it's a little bit different. For scattered radiation, the formula is a little different. What's going on here is that the X-rays are, actually I can, new toy. I'm going to show you that now. Let's get it up here. It's so I can show handwritten notes. So the scatter is this sort of situation. I have an X-ray tube above a table. The patient is on the table having the X-ray taken, and there's an image receptor beneath here. And so from overhead, here's my tube, here's my table. So the X-rays will approach the table, and then they'll be scattered in different directions. And so there are two distances. The distance for the primary radiation, so that's dP, and then the distance for the scattered, so how far it is from the point that we're interested in to the receptor we're interested in. That would be the ds. So, getting rid of my, so that's dP, the primary radiation distance, primary scattering distance. P is again permissible. We know W. Now, the use factor in NCRP 49 is always 1 for scatter. Scatter goes to in all directions, so we don't have any preferential. We're pointing at the scatter this way more often than that direction. Scatter is considered to be uniform, so the use factor is 1 for scatter. A here is the scatter fraction, and what that is, that represents is, I'm going to go back to my video, my notepad. Scatter fraction says if I have radiation incident on an object, and if this is a distance of 1 meter, and I measure 1 meter away, what is the fraction of that I measure here? I measure a certain dose rate here, Kermer rate. And I also have a dose rate that's at the point of scattering. Yeah, so the A is equal to the primary dose rate, the scatter dose rate divided by the primary dose rate. What fraction of the radiation that's incident scatters? So, and that fraction is A. So, let's that, go back to our, so these are the values that are published in NCRP 49. They're still used, although in a little slightly different way. It's really good data. So you can see that it's always about 1,000. It's a few times 1,000th. That's how much scatters. This is all based on a 400 square centimeter scattering area. So the beam that's reaching the patient, the phantom patient, and is scattering, that's 400 square centimeters, 20 by 20 centimeters. And so it scales by the surface area of the field. If the field is smaller, there's less radiation to scatter. If it's larger, there's more radiation to scatter. That's what this F is. It's the field size, the field area. And then once the scattering takes place, so we have this formula that tells us what the attenuated beam would be. It's the same thing. We set P is equal to our dose rate. K is our attenuated beam. Then we calculate what K is in terms of scatter. We go back and find out what thickness is required because of the scatter radiation. Now that's added on top of what we needed to attenuate the primary beam. Finally, there's leakage radiation based on the FDA rules. We know that the FDA allows 100 milliroentgen in any hour at 1 meter. So the NCRP 49 approach has a very conservative assumption. It assumes that this occurs at the rate of potential. So that 100 milliroentgen per hour is going to occur with the highest KB setting. That's more penetrating, more radiation will escape. So they assume you're at that highest setting, and so you're getting the 100 milliroentgen per hour or in an hour, and the highest tube current that's possible at that to continuously operate at that current that voltage. So, and it's continuously operating, so it's operating for 60 seconds a minute, and the 0.1 is figured here. That's why it's 100 or 600 instead of 60. That's that one over the 0.1. The leakage is in all directions, so the use factor is 1 also. So this is the formula for leakage radiation. We know our W. The facility tells us we have this many MA minutes per week. The occupancy that we're interested in, at the point we're interested in, is T. So this is done. And it turns out that in most cases, the HVL, or the leakage, is equal to our radiation from the scatter. And so if you simply add an HVL, it accounts for the leakage to whatever is determined for scatter. That accounts for the leakage. Excuse me. Okay, so that's the NCRP approach. Now, the new NCRP 147 approach builds on that, but updates it a bit. So we don't have, conceptually, we don't use this Kerma attenuated graph that we had before, where K involves the attenuation. Instead, the K is used for the attenuated beam always, and then there's separately in the calculations a barrier transmission factor, B of X. So that's how we're going to go about it. We're going to be finding out what the B of X needs to be, and from that, determining the X. We're not going to do it by solving the primary radiation, the output. Now, in NCRP 147, X-ray rooms often have a mix of procedures, and those procedures operate at different voltages. When we worked under ICRP 49, use one voltage curve. So we assumed that we use the voltage curve for whatever the procedure they did that had the highest voltage. That way it's a conservative assumption. NCRP 147 is based on surveys of facilities. They saw what kinds of mix of procedures are in the workload of the typical facility, and figured out what the total Kerma at a meter for all those different procedures are per patient. So they take all the patients in a facility, figure out what the Kerma would be from the X-ray tube for all those procedures, and then figure it out per patient. And so we can normalize it at different facilities based on the number of patients. We don't have to go count up how many different kinds of procedures and figure out the MA minutes from that. It's all done. It all works by statistics. So the Kerma, this is based on the Kerma per procedure and the number of procedures total in the facility or in the room. So as I note here on the third bullet, this K1 is based on the technique used for all of the procedures. And it is the KP is the primary beam with 0 attenuation, is KP of 1, KP per patient, K1, is the use factor. Again, how often do you point the X-ray tube at the barrier you're interested in? N is the number of patients, and D squared is how far from the primary, from the radiation source. And the Ks are normalized to 1 meter, so if you have the Ds in a meter, it all works out. Now this is what the unshielded dose rate. So the shielded dose rate is whatever the transmission factor is times the unshielded exposure rate. We're going to set that equal to P over T. That's how much radiation we're going to want at that point for the barrier we're interested in. P is the permissible dose rate, T is the occupancy factor. So if T is a half, this would be twice the permissible amount, because the person's only going to get, anyway, you get the idea. So the barrier factor, then, we can use these equations and turn them around. The barrier factor is P over T, D squared over the K1, U, and N. Okay, so this is a simple formula. We know all these pieces in the formula. Now, under NCRP 49, we didn't take any credit for any of the material that might have been before the barrier. The image receptor, the anti-scatter grid, the tabletop, the wall holder, whatever it was. But in NCRP 147, we can take advantage of those factors. So that transmission barrier we need is a function of X, but X is both the barrier we want to calculate plus whatever material is attenuates before the barrier. And there's a table in NCRP 147 that tells you what those are for different kinds of rooms. So that's what X-pre is. So we can, in NCRP 147, we can take credit for those and therefore sometimes use less shielding in the wall. Now, we've calculated this B. We based on all the parameters we know, but knowing what the transmission factor is, we need 10 to the minus 3. Doesn't tell us how much lead to use. So we need to go from B into turn that into the thickness. Okay. So here, one way to do this, there are several ways in NCRP 147. One way to do this is to use this equation. The thickness of your barrier is dependent on all these factors we know. The N we know, the T, the U, the K1, P, D squared, all those things. And then there's these parameters, alpha, beta, gamma. Alpha, beta, gamma represent that curve that we've seen, the attenuation that occurs. And so for different kinds of material at different tube potentials, these are the alpha, beta, and gamma. This is called the arch that fit data. There's no fundamental physics behind what alpha or beta or gamma in terms of the atomic number, the density of the material. They're just parameters that are. So these parameters, alpha, beta, gamma, are all available for lead, for different kinds of construction material. They're all available in the NCRP in an appendix. You can put those numbers into this equation, subtract away the X-pre, the image receptor, etc., and you figure out what you need as an X barrier. That's one approach. We can set up a spreadsheet, and so with all these different values into your spreadsheet, and so it could automatically figure this out. The next way to do this is to use a graph, similar to what we had before. Now, this graph is different from the one we had in NCRP 47 because this is not a function of different voltages. These are different types of X-ray rooms. A test room or a radiographic room or a radiographic and fluoroscopic room, etc. So we have the transmission that includes the mix of different kinds of procedures, and all the different kV settings um, uh, are used in the, so it's a little bit more realistic than the way we did before. So we calculate our B based on the things we know. It's the same formula I had here. Calculate the B. We go down here and say, I calculate I need a transmission of 10 to the minus 4. I go to 10 to the minus 4 and I move across and say, what kind of room is this? Oh, this is a uh, 4. I need a little bit more than 2.5, 2.6 millimeters of lead. Okay, for example. So this process is pretty easy. It is much simpler than the old way, because in the past we had to figure out those MA minutes. We had to figure out how many procedures do we do, how many hip procedures, how many KUBs, how many chest X-rays, how many MA minutes or mass do we take for each chest X-ray, how many mass do we take for each KUB. Add them all up and get the number of MA minutes per week. Now, all we need to do is know the number of patients we see a week. So that's a lot easier for the facility to provide accurate information. Um, let's see, for typical workloads, these kind of procedures that we've been talking about, then there's an even simpler way to do this. We calculate NT over PD squared. We get some number, and from that we can just directly go and get the lead thickness. If we've got any of these kinds of facilities, this is the way we can go about doing it. It's fairly straightforward. And the number of procedures, these graphs have the K built into them, is basically what it is. And so this is if we disregard that pre-shielding, that X pre. This is if we include the X pre, then that's why the graph is a little bit different, etc. This is for concrete. These were the CRP that are available. It's a fairly straightforward thing to do. Calculate NT over PD squared and then look it up in the graph. Now, in NCRP 147, we also have to address scatter radiation. The scatter fraction is similar to the one that's built on the one that we saw before in NCRP 49. The difference is the NCRP 49, the scatter was per 400 square centimeters of area. The scatter fraction they're using today is per square centimeter, not per 400. So that's calculated into these numbers. And also in the formula, remember when we looked at them before, it was about a factor of 1,000, 0.00 something. Now they use A as a whole digit, and we know that these digits are 10 to the minus 6. So they scale the A value and just put the 10 to the minus 6 into the formula. So the amount of radiation, the kerma, from scatter per patient is going to be proportional to the kerma from the primary radiation. It's proportional to the scatter fraction. Now, the scatter fractions, these are at different angles. So if I look at my room that I want to working on before, if I'm looking at a shield, so the tube is coming down. If I'm looking at a horizontal across the room, across the horizon, that would be a 90-degree scatter angle. If I'm looking for at some lower angle, it might be some other angle that we need to use to calculate. That's all based on where you're interested in calculating the dose. So you have to use the A value that's appropriate for where you're looking, where you want to calculate the dose at. That's what those A values are, a function of different. The highest A values are, the highest scattering occurs at backscattering, 140 degrees or so. Minimum is somewhere around 70 degrees or 80 degrees, 70 degrees, I'd say. So the kerma for the entire for the barrier at some point is related to the kerma per patient times a factor that relates to the for patients, then our A1 over our D. The DF is the F is the field size in square centimeters. DF is the distance after the scattering, or before the scattering, the distance from the X-ray tube to the scattering object, and then DS is the scattering, the distance from the scatterer to the point of interest where we're putting in the shielding. Okay, in addition, and so we have another formula here. There's the final P is going to be attenuated by a barrier factor B, and we're trying to find out the X that's associated with that. Radiation is similar to NCRP 147, except that NCRP 147, as I told you before, assumes the maximum leakage because they assume it's operating at the highest voltage. In NCRP, that's NCRP 49, excuse me. In NCRP 147, they take a more realistic look. They said they did all this work to find out what the KV settings are in a typical room, and they use that to calculate what the leakage would be given the regulatory limit. It's, if it emits 100 milliroentgen per hour at the highest voltage, it would emit less than that at a lower voltage. And so it takes account of that. And so our tables that tell us what it is. But most importantly, what we're most interested for secondary radiation is the sum of the scatter and the leakage. Okay. Now, in the NCRP 147, there are tables with this secondary radiation already calculated for you for these typical workload facilities that we talked about. It's in table 4.7. One thing to note when they do this calculation, they do the typical rooms, the typical workload rooms. They know how many procedures require lateral x-rays, how many procedures require vertical x-rays, so that the use factors are incorporated into the calculations they do for the typical workloads. If you think about it, the scattering, if the primary beam is oriented in one direction 50% of the time, then there's no scattering 50% of the time. Scatter is by definition outside of the primary beam. And so they have a 1 minus U that's incorporated in their calculations because there is no scattering for the fraction of time that the barrier is pointing toward the primary beam is pointing toward the barrier. Scatters only in other directions. Okay, here's table 4.7. So you can see that for different kinds of rooms, they tell you the most important thing is the leakage is calculated for those rooms. The scatter is calculated for those rooms. These are lateral, 90-degree angle. And then so the sum is presented here. And then for the forward and backward, that is these ends, low angle, high angle, they calculate the and the sum for the leakage is the same. There's scatter that's lateral, scatter that's forward and backward from the tube, and they give that sum for you as well. Okay, all the different kinds of rooms that they've calculated. So we have these are the K1s, right? That's what we're reading off of this table for the kind of room we have. That's the kerma per patient for secondary radiation. Well, then the unshielded, that's what the 0 represents. The unshielded kerma is just the kerma from one patient times the number of patients divided by the scattering distance squared. Okay. We can set put in a barrier factor, transmission factor, and set that all equal to the P, P over T, And then we can calculate what the barrier, we can invert that, find out what the barrier transmission factor is. Here's the formula that you get. You can calculate that. And then once you know what the required barrier factor is, you can do it the same way you did before. We had this formula where the Archer equation is fitted with these parameters. We can go use the same tables to look up the value of the barrier that's required there. There is no pre for scatter, X pre, no attenuation before the barrier for scatter, because it's by definition not toward the. There are graphs we can look up, again, just as we did before. If we know the N T P over PD squared, we can go to get the NT over PD squared, which are all in. Value is go up to the curve that has a kind of all barrier we're dealing with, and then move across laterally and find out how much lead is required, just like we did before. So that's the same thing we did before for secondary radiation. Okay. Now, what is the permissible dose? We've been talking about the P as a parameter. This part of the video, we're going to talk about these parameters and how do you choose the parameters to use. He has two possible values. If it's a controlled area, then P is set to 0.1 milligray per week. That's 100 millirem per week. This is a little 5 milligray per year. That's lower than the limit for workers, but does match the limit for a pregnant worker. The limit for pregnant worker is 500 milligray. 500 milligram is 5 milligray for the duration of the pregnancy. Uncontrolled areas, that is doses to members of the public, it's limited to 1 milligray per year, 100 millirem per year. So that's 0.02 milligray per week. And the other point to make, distances, permissible doses are evaluated 30 centimeters beyond the barrier. So that's a typical distance someone would stand away from a wall when they're functioning. Occupancy, T was another factor. T is sometimes the most difficult to decide. Occupancy is based on the work of the adjacent area. So if the room that we're shielding, that we're protecting, is an office or someplace that people work all the time, the occupancy factor is 1. It's a treatment room. People are in there part of the time. People are gone part of the time. The occupancy factor is 0.5. If it's a transient location, corridors, patient rooms, lounges, etc., occupancy is 0.2, 1/5. Now, I do want to make a point that these occupancies are for individuals. So, in a patient room, for example, someone might be there, 8 person might be there all the time, but the same person isn't there the entire year. The same person is only there for a fraction of the time, and that's why it's limited. As far as examination rooms, the person doing the exam, there are several people who do exams or procedures. It's not assigned to one person to be there all the time, and that's why the occupancy factor is set at 0.5. Corridors, corridor doors, so people standing in the doorway corridor is set as an occupancy factor of 1/8, 0.125. Other areas, public toilets, unattended vending areas, general public areas where people mill around is set at 1/20th, 0.05. And outdoor areas, sidewalks, vehicular, spend an inordinate amount of time at the same point, and that's why it's 1/40th. So those are the approved occupancy factors you'll read in this table from NCRP 147. Now, when we think about constructing the shield, after we specify the thickness, one thing to remember is that lead comes in specified thicknesses. They don't make this to order. So there is lead that is 32nd of an inch, 2 pounds per square feet, or it's um, pounds per square foot, 3 pounds per square foot. Those are the nominal thicknesses of lead. And so if you calculate something, you're rarely going to calculate something that's right on that value. So you move up to the next level that you. Um, when you're doing these designs, you need to specify details, things like door jambs to make sure that there's no gap in the lead. If you have a door and lead line wall, then the jamb around the door has to provide adequate shielding so that there's no streaming through the holes. You need to pay attention to the way that so that you don't have holes through it because of drywall screws. There are products that are designed specifically to prevent that. Penetrations for electrical or ventilation. In addition to doing the calculations, you need to prepare a report that documents the calculations. The requirements for that are specified in ICRP 147 as well. Okay, and that's what I have for slides today. Um, an example problem. And so here in Chapter 5 of NCRP 147, there are some example calculations. And so I'm going to do one right here, 5.2. Dedicated chest room. That's one of the types of facilities that's specified. And so it's a fairly simple one, so it'll be a pretty quick example for us. Okay, so let's see what they're telling us about this. I wrote down some notes. What we have here is a small x-ray room. Chest x-rays. And so a patient comes in, stands in front of the wall cassette, x-ray stops behind the barrier, takes the x-ray, patient leaves. And so the distance from the x-ray tube to the point we're interested in, 30 centimeters beyond the barrier, is 3 meters. So we're interested in scattered radiation, and so the distance to the point we're interested in from the scattering patient is 2.1 meters. They're specified in the problem. It also tells us that you can see here that they do 100 patients per week. That's their workload. So n is equal to 300. We have the primary beam distance is 3 meters. Secondary beam distance is 2.1 meters. So now we have to make some decisions. What's the use factor? Well, this is a dedicated chest room. The use factor is in that direction. It doesn't do a bunch of different procedures. What's the permissible dose rate here? Well, we're going to say this is an office. It's an uncontrolled area. And two per week. Occupancy factor, well, it's an office, so that's 1. If it was a storage room, however, I think I should mention that when you're designing these, don't consider only how they're using the room right now. It may be a little bit cheaper, but later on they may turn that storage room into an office, and then you won't have adequate shielding to protect the person. Okay, so how do we go about doing this? Well, let's go to our slides. We can either go to our slides or go to it in here. Was KP0 NU over D. the formula we had in our slide. And so you unshielded them out. Then we also know that our required barrier to P over T, K1PUN. That's the formula we use. So we know all these values now, except for the K1. So I mentioned before, we get the K1 from a table right. This is the K1P, primary beam K1 for, we're doing a chest room and right here, 1.2. So the K1P for chest room is 1.2. So that's, the P was 0.02, the T was 1, P squared was 3, so that's 9. Uh, Calculator, 0.2 divided by 300. You can see it there, 5 times 10 to the minus 4. That's the barrier factor we need for the primary barrier. Okay, let's go look that up. And so we go to the factor was 5 times 10 to the minus 4. 10 to the minus 4. There's 5 times 10 to the minus 4. Go all the way over to the chest room. 5. That's 5 times 10 to the minus 4. Right? So that's the value. I would say that's 2.15 millimeters of lead. Does that look right to you? Okay. Now, X pre. So we have, that's our total X. Now, how much credit do we get for this wall bucky, the wall holder? That was, I showed you those. They were back in section 4. There it is. So, image receptor for wall-mounted cassette holder. Okay, is 0.85 millimeters. How much do we need it to be in the barrier? It's the difference between those, and that is okay. Now let's think about scatter. Sidewall. How much lead do we need in the sidewall? Okay. Well, we have a distance. So our formula for that is very similar. Let's see. It was on this table. So let me rotate this. See, so we have a chest room right here, and we want the this is going to be sideways scatter, right? So this is leakage and sideways scatter. So it's this one, 2.7 times 10 to the minus 3. And so our B secondary of that is equal to was P over T, D squared secondary over K1 secondary times N. Okay, now 0.02, T is 1, D squared, I just said it was 2.1 squared, right? K is 2.7 times 10 to the minus 3, and N is 300. And let's multiply those out. What is 10 to the minus times 2.1 times 10 to the minus 3. More closer to it is 0.10. Now, we go back to our appendix. Let's view back. Okay. 109. Is our attenuation. There we transmission secondary radiation through lead. There, transmission secondary radiation through lead. There it is. So we had a B of our B was 0.109, 0.11. So 0.1 right here. Here's our chest room. It's 0.1. So about 0.45 millimeters. This is the side wall. It needs only 0.45. Now, let's look at the to us. Um, so we can get 1.3 millimeters. I got a 1 millimeter is not enough. 1.19 is not enough for what we needed there. So it would be a 4-pound ladder, 1/16 of an inch. Now 0.45 is less than we can use a 32nd of an inch for that. That's what we would specify. Well, not 6, it was the 16th of an inch. Okay. Okay. Well, that's what we have for. So now I have shown you examples. I've shown you in RP 147 where examples are. They're in chapter 5. If you need to look for more, there are examples of all the different. You will see. Let me show you. It can get more complicated than what we did. So we did the wall bucky. That was a simple one. You can see, for example, when they look, see that there are adjacent rooms. There's rooms below, rooms above. Okay, and all this is worked out for the radiographic floor. They've got the ceiling. They've got all the walls, and so those are all available to you should you need help. Now, NCRP reports are available for purchase as PDFs or as documents. Time is short, so waiting takes some time. But I did notice that I will pass along to you that let's just go. There we go. Go to my, use that one. And if I Googled NCRP 147 P, not ODF, we want PDF. Some people have published it on the web. Example, this one may have. Oh yeah. Oh, these are slides. But they're also. This is one of the guys who wrote it. First link provides. So you can find all this available, and other resources. So you can find out. So you can see the link, and hey, that's what I have to tell you today. Please get in touch with me if you have any questions or concerns. You need to go in and grade midterm exams this weekend so that you'll know where you stand. And then these kinds of calculations is what I thought would be the best thing to do for the final exam. If you have questions about that, this is short notice. Talk to me and I'll see what I can work out. Thank you all. It's been a wonderful semester working with you. Bye-bye.